Today we're gonna so let's get started. When folded up, find all the other vertices that meet with vertex 1 in the following nets. Over here we have all the vertices. Some aren't that well shown, so we made it more black so you guys can see. Anyways, let's find all the vertices that meet with vertex 1 in the following nets. Alright, so what do we do? Well, in this problem, what we can do is draw some lines. Since we use lines to find the intersections. As we talked about before in last class, if we draw a diagonal of a 1 by 2 like this, we can find the ones that intersect. In this case, we can say we can draw here to here. If these can be connected by a path of diagonals like this, then these must intersect. So this vertice must intersect. And you could do it similarly for the other ones, like this. Or you might do it like this, which is the exact same thing as before. Or you guys might do it like this. Basically, we're trying to find as much diagonals like this that fit on here, but it's connected to the path, basically. For example, we have this one over here. We draw the first diagonal, then we draw the second, and then we draw the third, and then we draw the fourth. Right? So it continues lines all up. Right? For example, and for this one, in this case, we can draw like this. We can also draw from here or to there, right? We can continue it to this one, which is basically about the same thing. We can continue it like this, or we can draw this. And you get the idea for the rest of the ones. Alright? So basically, to find all the vertices that meet up with vertex 1, we just draw the 1 by 2 diagonals and then connect them so that most of them are connected into a path. Like for example, this is a path, or this is a path also. Right? Now let's move on to problem 15. When folded to form a cube, what is the value of in the square opposite of the one marked x? Let's give it a try on this question and tell me answers to chat. All right, let's get started with this question. So obviously, as we talked about last class, there's two ways to approach this. One, to make an actual cube with the exact same layout. You actually can cut it out from paper, fold it, and make a cube, or you can just imagine it with yourself. If we imagine it, notice that if we can flip 3 and x like this. So we draw the cube. When we draw the cube, when we flip it, we have 4 at the bottom, x over here on the side, 3 as the center face over here. You know what? I'll draw in blue. This line. This is 3. All right. Now, what is this? What is this side length? Well, if we imagine it, since we flip three right over here, right? We flip three this way, right? Flips it this way. Now this two will also be flipped over. And then extend it like this. So naturally, we will fold it in. So after we flip, we can fold this in to get to over here. From there, we notice that that's the opposite of x, which is just 2 or b. All right. Now let's move on to 16. Find the sum of the numbers of triangle faces that share the same vertex as A. I'll let I'll just got to try this question and send message to private chat, please. Alright, guys, so basically, how do we approach this? Well, notice that we first draw these diagonals, right? Well, when we draw it out, the ones that intersect come from these vertexes, not these. These do not intersect. Because clearly, when this is an octahedron, if I'm pretty sure, if it's correct, correct me if I'm wrong. But you clearly can see when we fold it up together, these will not be intersecting. These will not be intersecting. You can clearly see. So it must be these intersection points. It's become 7 plus 5 plus 1 plus 3, which is just 7 plus 5. 7 plus 4 plus 5. This is 4 and this is 5. And which gives you 16. Right? So the answer is C, or 16, and it's not 17. Right? Be careful about these points because these do not intersect. Like you can say these do not intersect, which means that this also does not intersect with that. But we know these intersect, so it means that A does not intersect with this point. Alright? Now let's move on to problem 17. If a strip of triangles, as shown, is folded to form an octahedron, and each vertex is assigned the value of the sum of the four triangular faces to which it belongs, find the maximum value of the vertex, of a vertex. I was going to try to answer this question and tell me this through chat. All right, guys, let's get started with this question. So we already know that there's already three faces that meet at vertex A, 8, 7, 6. So we only need to find one more face. All right? We already know that these are already true, since they are the biggest numbers here. Now, we only need to find one more face. Vertex B will meet vertex A when floated, right? So I'll draw B and A. B is over here, and A is over here. An important place, right? So the other face will be marked 3. This will be marked 3. It's simple to see that 8, 7, 6 all interact together. And from there, so we can draw these diagonals or these lines to help connect to get 8, 7, 6 and 3 intersect together. So it means the maximum value is 8 plus 7 plus 6 plus 3 or 24 or E. Alright? Now let's move on to problem 18. When the strip of triangles is folded to form an octahedron, which face is opposite the shaded one? I'll let you guys have a try on this question and try to answer the chat. And by the way, this is the shaded one. I'll shade it in real quick. There you go. I'll just go to try on this question and tell me the answer to chat. Alright, guys, let's get started with this question. So how do we approach this? Well, from here, what do we do? Well, how many ways are there to do this? Well, we start with this. This is the shaded vertex. I'm not gonna shade it. I'm just gonna put a highlight mark there. From here, notice that we can draw the diagonals that we drew before. These all intersect, alright? So these, so this face, this point right here, intersects with this point right here and this point right here. And then we can find out this point right here, draw it to here, and draw it to here. Will intersect. From here, you notice that these clearly, there's only one place where there's two that both three, actually, or three, these are actually opposite. These are the same. Since these both intersect on this triangle, C, we can know that these are opposite because since these both intersect and it's not alternating, from here we just notice that, oh, they share the exact same vertices. So basically, we know that this is opposite, right? This is an octahedron looks like this. And from here, you're going to see this is like this. We know is since these all intersect together in one side, they should be opposite of each other, right? Okay, what's your question? Alright, if there's no questions, then let's move on. Answer this question, just C. Problem 19. An octahedral net is a collection of adjoining triangles that can be folded into regular octahedrons. When the net below is folded to form adjacent to one marked with a 3, when the net below is folded to form an octahedron, what is the sum of the numbers on the faces adjacent to the one marked with a 3? Let's try this question and tell me through chat. You may annotate the screen if you want, if it helps you do it better. All right, let's get started with this question. So basically, we're gonna find some of the numbers that are adjacent, faces adjacent to the one marked with 3. How do we find this? Same thing as here, we just draw the diagonals. Or the lines going past 2 triangles. Draw all possible after we go from here. Draw all possible lines. From here, there's only one, only, from here, there's only 3. So from here, we get 3, if I'm correct. Oh, wait. Oops. From here, there he is. Let me see it correctly. Yep. From here, there's 8. Since this is literally adjacent. The faces are literally adjacent. Already adjacent. 7, since we can draw it and we see the vertices connect, so this must be adjacent. So this is 1. 1 works. And so is 6, since you connect it and you get 6 shares of vertex. So it'd be 8 plus 6 plus 1, or 15, or B. Alright? Now let's move on to problem 20. An octahedral net is a collection of adjoining triangles that can be folded into a regular octahedron. When the net below is folded to form an octahedron, what is the sum of the numbers on the faces adjacent to one marked with a 4? So you guys have a try on this question and tell me to chat. All right, guys, let's just start with this question. So I think I gave you guys enough time to go over it and think about the question and how do we solve it. So, what is the nebula when formed? What is the sum of the here with the mark with 4? Right? Where's the 4? The 4 in this case is over here. Right? So exact same method as we did before, we just draw all possible diagonals. Right? From here, we analyze this. So from the figure, we see that these two will both meet, as obviously we get after we draw the lines. So we know that the faces 2, 5, 6, 4 will share the same vertex. We also know that face 1 is also adjacent to face 4. And we see that the red lines going through both face 4 and face 5. As you can see over here. Or in this case, black lines. Since face 2 is adjacent to face 5, it must not be adjacent to face 4. So face 6 has to be adjacent to face 4. Why? Because face 2 is adjacent to face 5, but cannot be the exact same thing as face 4. Right? This is not correct. So be 5 and 4. So 5 is adjacent to 4. 1 is also clearly adjacent to 4, which results in 6 is also adjacent to 4. Which means the answer is 6 plus 5 plus 1, or E, or 12. Now let's move on to problem 21. Then this net with 5 square faces and 10 equilateral triangles faces is folded into a 15 face polyhedron. How many edges does the polyhedron have? I'll let you guys have a try on this question and tell me the answer to chat. All right, let's get started with this question. So basically, how do we approach this? Well, how do we find how many edges are there? Well, let's first find how many vertices. That's the most important part. Or let's draw it first. So what happens when we draw it? It'll turn out to be like this, right? Someone look like this, and then the end is the exact same as the top. It looks like this. Remember the edges and face formula, which says edges is equal to faces times side length, sides divided by 2. And faces times, well, what is S? It's just faces times vertices, right? Just remember that. That's the important part. It's edges is equal to faces times sides divided by 2. So in this case, how many sides, how many squares are there? There's 5 squares. And each have 4 sides. Adding on to the 10 triangles with 3 sides each. Divide by 2. Doing all of this calculation gives you 25 or B. Important to memorize or how to know how to derive these formulas. So it can help you anywhere. So in this case, edges is basically the faces times the number of sides. In this case, it's not quite faces times the number of sides, since we just find the total number of sides in every single polygon, add them all up, and divide by 2 to find the number of edges. Alright? The answer to this question is just B or 25. Now let's move on to problem 22. A convex polyhedron has 36 faces, 24 of which are triangular, and 12 of which are quadrilaterals. Find the number of space diagonals the polyhedron has. A space diagonal is a segment connecting two vertices which do not belong to the same face. I'll let you guys have a try on this question and turn this to chat. Alright, let's get started with this question. So basically, how do we approach this? Well, notice that the number of faces is 36. By the edges in face formula, which is f faces times the size per face, divided by 2, you can get that there's 24 times 3 plus 12 times 4 divided by 2, which is equal to 60. That's the number of edges. Now, we know from Euler's formula, we talked about before, at the faces plus vertices is equal to edges divided by plus 2. Edges plus 2, not divided. Plugging in our values, we get vertices is equal to 26. Alright. Since each quadrilateral has two face diagonals, each quadrilateral has two face diagonals, we get there's 2 times 12, since there's 12 quadrilaterals, 24 face diagonals. Now notice that we talked about before was combinatorics. The number of ways to choose two vertices from 26 is 26 choose 2, which tells us the amount of space diagonals, including face diagonals, but we only want space diagonals, not face diagonals. So we have to subtract the extra 24 to get the answer of 241. And also, don't forget to subtract the 60. I forgot about that. My bad to add it in. 60 is 241. So 60 is also just adjacent vertices. Right? The answer to this question is just D. Alright? So that's it for today's class. I hope you guys have a wonderful weekend, and I'll see you next week. Bye!